Good evening. I'm Spot On Weather meteorologist Matthew Euler, and we're going to start into another topic tonight. Going to go over another weather training topic in the summer weather training series. The last time we talked a lot about the global circulation of the high and low pressure belts across the globe, the specific latitudes, highs and lows generally set up. And today we're going to kind of bring it in a little bit closer from the larger global scale to now more of a synoptic scale. And we're going to talk about various pressure systems. Of course, most of us are familiar with the high pressure systems and the low pressure systems of the mid-latitudes and how they move from west to east with the jet stream blowing from west to east and pushing them along. So we're very familiar with these, with the very changeable weather in the mid-latitudes. So we're going to have a lot of interesting things to say here tonight on the training video. So let's get started. All right, we're going to start off with the pressure system overview. Just a couple main bullets here to really get you introduced to pressure systems as a whole. First of all, in wintertime, there are large high pressure areas that generally form over the colder land, and lower pressure areas tend to form over the relatively warm oceans. In summer, this pressure pattern reverses, where we now get highs forming primarily over water and lows forming over the heated land areas. So things kind of switch around between winter and summer. That difference in heating and cooling of both land and water surfaces, that's known as the thermal effect. And it plays a large role in determining where highs and low pressure systems are going to be throughout the year. The dynamic effect, this relates to circulation systems that are created by the interaction of wind belts of pressure systems or the variation in wind in combination with certain distributions of temperature and moisture. And most systems in general are created by a combination of the differences in heating and cooling of land and water, as well as the dynamic effects. When we talk about dynamic effects, that happens quite frequently in the mid-latitudes specifically. And so if the Earth, we talked about last time with, again, the global circulation pressure patterns, these smaller scale, synoptic scale lows and high pressure systems are where they're generally set up throughout the year. Those are caused a lot because of the land and water thermal effect. So the pressure belts of the general circulation, these are broken up into detached areas of high and low pressure cells. And these cells tend to persist in a particular area and are called centers of action. Sometimes you may have heard these referred to as semi-permanent. Semi-permanent meaning that they generally set up in the same location across the globe throughout the course of the year. And I'll show you a great map here in a moment. So being that they're found at nearly the same location with similar intensity during the same month each year, again, we'll get into that here momentarily. Now, the permanent belt of low pressure along the equator and another deeper belt of low pressure paralleling the coast of Antarctica occurs in the southern hemisphere. And there's permanent belts of high pressure which largely encircle the Earth, generally over the oceans in both the northern and southern hemispheres. Now, regions where the pressure is predominantly low or high at certain seasons, but not throughout the year, I'm going to go through those pressure systems. Also in the vicinity of Iceland and near Alaska, the Icelandic and Aleutian low pressure systems are strongest during the winter season. So these pressure systems change in intensity from summer to winter, with the Icelandic and the Aleutian low near Alaska being strongest during the winter season when you have the largest temperature contrast between the cooler land and the relatively mild water. And again, there's two areas of semi-permanent high pressure systems which also exist. There's one over the Pacific Ocean, west of California, and there's another semi-permanent high pressure area over the Atlantic, and that's near the Azores off the coast of Africa. Now, these are known as subtropical highs, and they play a large role in the type of weather that we see from the west coast to the east coast. They're more intense, they're farther poleward, and cover a greater area during the summertime. And these subtropical highs, they tend to move equatorward or towards closer to the equator, and they weaken in the wintertime when the jet stream strengthens and it dips down into the middle latitudes much more frequently. Now, the largest individual circulation cells in the northern hemisphere are the Asiatic high in the wintertime and the Asiatic low in summertime. In winter, the Asiatic or Asian continent is a region of strong cooling, strong radiational cooling, and therefore is dominated by this large high pressure cell. In the summer, strong heating is present, and the high pressure cell becomes an actual large low pressure cell. So again, things reverse between seasons. This seasonal change in pressure gives rise to the monsoon flow over India and Southeast Asia, and I'll go into that closer to the end of this presentation, the monsoon, and kind of show you the graphics and the causes behind that. Now, both the Arctic and the Antarctic highs have considerable variations in pressure. For example, the Greenland high is a persistent feature, but it is not a well-defined high during all seasons of the year. So here's a map of the average annual pressure distribution. Now, I am just taking this throughout the year. This is generally where you find average areas of lower pressure, average areas of higher pressure. All right, so a couple main bullets we need to take a look at on this map. First, along the equator, there's a belt of relatively low pressure, which is encircling the globe with barometric pressure of about 1012 millibars, On either side of this low pressure belt is a belt of high pressure, and this high pressure area in the northern hemisphere lies between 30 and 40 degrees north latitude, and there's three well-defined centers of maximum pressure over the oceans. One is over the eastern Pacific Ocean, one is over the Azores, and the third is over Siberia, which averages about 1020 millibars. Now, if you notice on this chart as well, the pressure is going to lower or diminish as you get closer toward the polar areas. Now, there's extreme pressure differences, especially over the Asiatic continent. The pressure can range from 999 to 1033 millibars on average over the course of the year. So a big difference. Now, over North America, the most significant feature is high pressure in winter, where you get these cold highs that come down from far northern latitudes and land masses up to the north. Western Canada, central Canada, down to the U.S., while the heat low dominates over the southwestern U.S. in the summer season. All right, so this is just a general distribution of pressures. The intensity of these systems does vary between the seasons. Now, I wanted to break this down even further and show you a January pressure distribution on the left and a July pressure distribution on the right. And you'll notice in January how the areas of lower pressure up towards the Gulf of Alaska or the Aleutian Islands, that's much more intense, it's much stronger, as well as the Icelandic low in the vicinity right there between Greenland and Iceland, much more intense during January when we have a much larger temperature contrast, a more energetic jet stream. We get this huge temperature contrast which drives a jet stream from very cold land in the high northern land areas in winter and the relatively warmer waters. And so there's this huge areas of low pressure set up, generally around 60 degrees north latitude, again, Icelandic low and the Aleutian low or the Alaskan low. You'll notice also on the graphic on the left how the high pressure systems over the oceans, they move closer to the equator and they become much weaker. Additionally, you'll notice that little red dashed line actually in both graphics here, and that's indicative of what's known as the ITCZ, or the Intertropical Convergence Zone. This is typically a line of discontinuous thunderstorms that occurs year-round. The ITCZ does move further south in January. It's like it follows the sun. It does move further north in the summer, the Northern Hemisphere summer. And so the ITCZ, why is this important? This is the area at which air converges from both hemispheres. Southeast trade winds and the northeast trade winds converge, and when those two converge, the air rises and we get areas of thunderstorms or disturbed weather that form. And sometimes those areas of disturbed weather can actually become tropical cyclones. So it's always interesting to look at the global satellite images, and look at that discontinuous area of showers and thunderstorms on the satellite, those higher cloud tops, and to see if anything is going on. All right, moving over to the graphic on the right. Now look at the differences in the northern hemisphere. Now we have a much more significant, stronger East Pacific high, and then you also have a much stronger Bermuda high. And these two play significant roles in the weather in the U.S. For example, on the west coast of the U.S., when these high pressures, when the Pacific high strengthens in summer, you generally have a mild summer. It's not super hot, all the way down from Oregon, Washington State, Oregon, and California. And so on the east side of the Pacific high, you get more of a northwesterly wind along the coast, and that results in more stable air. Marine layer and low clouds and fog is much more common in July across the west coast. Meanwhile, the July time period when the Bermuda high expands to the north and also ridges its way westward into the southeast and mid-Atlantic coast, it's very muggy because you have the Bermuda high, and on the backside of the Bermuda high, you have a much milder south-southwest wind regime, and that results in that muggy humidity of the east coast, the eastern seaboard, up to New England. Notice again that the ITCZ on the graphic on the right in July, look how much further north that ITCZ line is. And again, that is the birthplace of tropical cyclones, so we're always keeping an eye on that. And also keep in mind that, January is winter in the northern hemisphere, but it's the opposite season for our friends, let's say in Australia in the southern hemisphere, or points south of the equator. And the opposite occurs in July. When it's our summer, it's their winter. Right, so now we're going to talk more specifically about the pressure systems themselves. We're going to just do a brief overview of what an anticyclone is. This is an area of relatively high pressure with a clockwise flow in the northern hemisphere. So the winds are going to turn and spin clockwise around the anticyclone. Counterclockwise, the opposite direction in the southern hemisphere. And the major point to note here is the wind flow is going to be slightly across those isobars, or lines of equal pressure, and outward and away from the center. Now, anticyclones typically bring you nice weather, fair weather. Now, the formation or intensification of an anticyclone, this is a fancy name. It's called anticyclogenesis. It's just saying that an anticyclone is either forming or getting stronger. Now, when a high pressure center is increasing in pressure, we say the high is building or intensifying. Now, what happens when the anticyclonic circulation weakens? We call this anticyclolysis. And when the pressure of a high is decreasing, the high is actually termed weakening. Now, the vertical extent of pressure is going to depend on the air temperature. And I'll show you some great graphics as we break down the warm core versus cold core pressure system soon. Pressure is going to decrease or get lower more rapidly in the vertical in a column of colder air as compared to warmer air. And in a cold anticyclone such as the Siberian high during the northern hemisphere winter, the vertical extent is going to be shallow. Again, I'll show you that soon. In a warm anticyclone, on the other hand, such as a subtropical high, the Bermuda high or the eastern Pacific high, the vertical extent reaches far up into the upper atmosphere due to the slow decrease in temperature with height. Temperatures are going to cool much less rapidly with height in association with a subtropical high. Now, what about cyclones? We've heard this term before, and I'm sure you've heard it before on TV weather by the TV meteorologist. A cyclone is simply a circular or nearly circular area of low pressure with a counterclockwise flow. In the northern hemisphere, it's counterclockwise. Now, in the southern hemisphere, the flow would be the opposite, or clockwise. Now, the wind flow is slightly across the isobars, but you notice the dark arrows here on the diagram. The wind tends to blow inward towards the center of the low pressure system. It's commonly called a low, or sometimes you may hear somebody call it a depression. Now, cyclones have their own terms, unique terms associated with them, just like anticyclones did. For example, the formation or intensification of the cyclone, that's known as cyclogenesis. Whereas when the pressure in the low is falling, we say that low is deepening. Now, the decrease or eventual dissipation of a cyclone, that's called cyclolysis. And I always thought about cyclolysis as some kind of evil villain character. You know, you can look at it any way you want. You know, whether you do Marvel or, you know, if you're a child of the 80s, you remember like some of the old action figures that used to be out. Cyclolysis. It just, for some reason, always makes me think of like some kind of villain in a superhero movie or something. Anyway, when that pressure in the low is rising, we call that filling. We say the low is filling. And then cyclones in the middle latitudes are referred to as extratropical cyclones. Extra literally meaning outside the tropics. The term tropical cyclone refers to both hurricanes and typhoons. And it depends on the location, of course. If you're west of 180 degrees west longitude, then we call it typhoons in the western Pacific. If you are east of 180 degrees west longitude and also in the central, in the Atlantic, the Gulf of Mexico, and Caribbean, they're known as hurricanes. Now, what about the vertical structure of pressure systems? Basically, to better understand the nature of the pressure systems, it is necessary to consider them from a three-dimensional standpoint. And I've said this before in my previous training videos. The atmosphere, you have to look at it not only in a two-dimensional aspect, but in a three-dimensional aspect, in the vertical as well as a horizontal. Now, with the aid of surface and upper air charts, you will see that there's a relationship amongst those three dimensions of the pressure systems within the troposphere into the lower stratosphere. Now, keep in mind, the troposphere is the layer at which all weather occurs, and it's basically from the surface, extends upward aloft. The second layer of the atmosphere above the troposphere is known as the stratosphere. Now, the thickness of a layer between two isobaric or constant pressure surfaces is directly proportional to that mean or average virtual temperature of the layer. Now, that mean virtual temperature, that's the average temperature at which dry air would have the same pressure and density as moist air. Now, keep this in mind. Why do we use virtual temperature? You know, what is the difference between virtual temperature and regular temperature? Virtual temperature takes into account both the temperature itself as well as the moisture within a column of air. And that's very important as far as determining the distance between two isobaric surfaces or constant pressure surfaces. Okay? Because moist air, the more moist the air, the much further apart those constant pressure surfaces are going to be, more expansive the atmosphere, right? If we have a dry air column, on the other hand, we're going to have a much more compact, shorter distance between two isobaric surfaces. So it's very important to look at the virtual temperature, not just regular temperature, but virtual, accounting for both moisture and temperature itself. Now, the higher the mean virtual temperature, the thicker the layer and vice versa. Now, I'm going to show you some examples. Now, we talk about three dimensions of the atmosphere. I want you to pay attention to the fact that on the bottom of the graphic here, I'm showing surface pressure. I'm showing a surface low pressure area and as well as a surface warm front and a cold front. The warm front is denoted by the red line with the semicircles on it, and the cold front is the blue line with the triangles. Now, if we go up in the atmosphere above these surface pressure features, okay, we go up, the upper levels of the atmosphere are going to support the further development of this area of low pressure at the surface through processes such as divergence, where the air spreads apart over the surface low. And so what I want you to get from this slide is that we not only pay attention to the surface, but we also look at various levels above the surface, such as 10,000 feet above the ground, 18,000 feet above the ground, up at the jet stream level, even as high as that, up at 30,000 feet above the ground. That all connects. It's all tied in together from the surface all the way up the upper atmosphere. If we look at two columns here in the graphic, you'll notice that the one on the left is shorter. It's not as tall as the one on the right. And this is due to that higher mean virtual temperature. That column or thickness or vertical distance of the column on the right is going to be much greater. So let's look at the column on the right. You see that due to its higher mean vertical temperature, the thickness or vertical distance between the layers, between that surface at point P and the top of the column at point P5 are much greater in the warmer column as compared to that colder column on the left. What I want to go to now is I want to go into the different types of highs and lows, cold core versus warm core. So we'll start with the cold core high. The cold core high is one in which the temperature on a horizontal plane decreases toward the center. So you got the coldest temperatures towards the center of this high. Due to the coldest temperatures at its center, the vertical spacing of these isobars or lines of equal pressure in the center, it's going to be much more tightly packed or closer than on the outside. Surface pressure is highest due to the densest, coldest air being in the center of the cold core high. However, the pressure rapidly will decrease with height, and I mentioned this earlier, that in a cold column of air, that the pressure decreases much more rapidly with height as compared to a warm column. So these highs, these cold core highs, are quite shallow with an upper level low typically located above them. If you look at the graphic in the upper right portion of the slide, you'll notice there's a high pressure area denoted by the H, letter H, and you'll notice above that there's a letter L, and that indicates a upper low situated above the cold core surface high. And you notice the spacing of these solid dark lines. Again, you note how much more tightly packed those solid black lines, those constant pressure surfaces are at the center of the cold core high as compared to the outer edges of it. Right, so if the cold core high undergoes any kind of warming from below, or let's say strong subsidence or sinking air motion, it diminishes rapidly in intensity over time. So, the common case of this occurs in the wintertime in the U.S., where you initially have a very cold core high, very cold high that comes down out of Canada, and it's very strong over Montana and over the northern plains. But as this cold core high transitions southeastward into the Midwest, Ohio Valley, eventually the Mid-Atlantic, or even the Southeast, the cold core high is going to modify very quickly due to warming from below of the landmass. So its intensity does change over time. Thickness is relatively low with the cold core high, sloping toward the cold air aloft. And anticyclones are found in Arctic air, and they're always cold core in this case. Examples include the North American high as well as the Siberian high in the wintertime. That's an example of cold core highs. Now what about warm core highs? This is the opposite effect. A warm core high is one in which the temperature on a horizontal level is going to actually increase or get warmer towards the center. These are those expansive heat domes, and if you look at the upper right-hand graphic, you have a expansive heat dome. You see how it almost forms an inverted U-shaped pattern? And so you have a surface warm core high, and above it you have high pressure as well. So you have extremely high heights in the center of these. All right, because temperatures in the center of the warm core high are higher, or highest, the vertical spacing of isobars in the center is farthest apart than on the outside. So look at the solid black lines again, the upper right-hand diagram there. You notice how the spacing of those constant pressure surfaces are farther apart at the center of a warm core high. Now, a warm core high increases in intensity with height and has an anticyclonic or high circulation at all levels. The warm core highs are going to slope toward the warmest air aloft. And examples of warm core highs include subtropical highs such as the Azores, or it's also known as the Bermuda High in the Atlantic, and the Pacific High in, obviously, the Pacific Ocean. So, big difference in the spacing. If you look at the graphics the upper right, between a cold core high, much more shallow, much weaker with height. You usually have upper level low over it. Coldest temperatures at the center, tightest packing. Warm core highs, opposite. Much more expansive. High pressure over surface high pressure. Now, cold core lows contain the coldest air at its center throughout the troposphere, going outward in any direction at any level in the troposphere. Warmer air is encountered if you go outward. So cold core lows contain, again, the coldest temperatures at its center. Now, cold core lows increase in intensity with height. Their relative minimums and thickness values, typically these are called cold pools. This is where they're found. So cold core upper level low, you might see that spinning for days on end, especially during the winter time. The temperature distribution is almost always symmetrical or circular in shape, with the axis of the low nearly stacked vertically. Now when they do slope vertically, the cold core lows slope toward the coldest temperatures aloft, and the lowest temperatures, again, coincide with the lowest pressure, because that's where you have your density decreasing most rapidly. The cold core low has a more intense circulation actually aloft, above the surface, from 850 to 400 millibars. So about 850 is about 5,000 feet above the ground. 400 millibars is above 20,000 feet above the ground. So they're more intense in that specific layer above the ground. Cyclonic circulation aloft is usually reflected on the surface in an abnormally low daily mean temperature, often accompanied by instability and showery precipitation. When you get these cold core upper lows, they tend to lead to instability and more showery precipitation. Sometimes you get thunderstorms with them as well. Now, the Aleutian and Icelandic lows are examples of these cold core lows, and occluded cyclones are generally cold core in their latter stages as polar Arctic air has closed in on them and got wrapped into the circulation. An occluded cyclone is basically one in which the storm is weakening. It's a weakening cyclone. Look at the graphic in the upper right with a cold core low. Notice that you have an upper level low, represented by the letter L, above the surface low. And again, the intensity increases with height. Warm core low will decrease intensity with height, and the temperature increases toward the center on a horizontal plane. So we have the warmest temperatures towards the center. It's frequently stationary, such as a heat low over the southwestern U.S. in the summertime. Heat low is formed as a result of the intense land heating beneath it. Also found in its moving form as a stable wave along a frontal surface, so that's also a warm core low. There is no warm low aloft in the troposphere. A tropical cyclone is a warm core low as it slopes towards warm air aloft. So tropical cyclones are a great example of warm core lows. Now, a warm core low will decrease in intensity with height or completely disappears, being replaced by an anticyclone or high pressure aloft. The heat low of the southwestern U.S., Asia, and Africa are all examples of warm core lows. Now look at the spacing of the diagram upper right. With the warmest temperatures at the center of this low pressure, you get the greatest spacing between these constant pressure surfaces with solid dark lines, and you typically have a high pressure system aloft over the surface warm core low. Now let's move into a discussion on dynamic lows and dynamic highs. Now these are different than what we've talked about previously with some of these cold core, warm core lows and high pressure systems. Dynamic lows are systems that retain their closed circulations to appreciable altitudes or elevation and are migratory. They move. A dynamic low is a combination of a warm surface low and a cold upper low or trough, or a warm surface low in combination with a dynamic mechanism aloft for producing a cold upper low or trough. With a dynamic low, the axis is going to slope towards the coldest tropospheric air, and after occlusion or weakening of this low, the dynamic low becomes a cold low with the axis of the low becoming vertically stacked. A dynamic high, on the other hand, this is a combination of a surface cold high and an upper level warm high or a well-developed ridge, or a combination of a surface cold high with a dynamic mechanism aloft for producing high-level anticyclogenesis. And when I talk about dynamic, both the low and the high, I want you to think about the high and low pressure systems that move across the United States, those associated with the jet stream. Now, the axis of a dynamic high is going to slope toward the warmest tropospheric air. So you notice the dynamic low, the axis slopes towards the coldest air aloft. Dynamic high, it slopes towards the warmest tropospheric air. And in the final stages of warming, the cold surface high, the dynamic high becomes a high with the axis stacked vertically. If we look at the lower right-hand graphic, I'm showing dashed lines. Those dashed lines represent thickness values, and the letter H represents the letter H represents high pressure systems, the letter L represents low pressure. And the solid lines represent the surface feature, and the dashed lines surrounding the low and high represent the upper level feature. And with the low, for example, you notice that the surface low is to the southeast. It's located to the southeast of the upper level low. And the surface high is located to the northeast of the upper high. So these systems tend to really rely on the jet stream for energy, temperature contrast, especially in wintertime. Really energize dynamic lows and dynamic highs. Now let's move into a couple more different circulations associated with pressure. One is the monsoon circulation, and then I'll end tonight's training with a discussion on the land and sea breeze. So the monsoon, what does that mean? The term monsoon is actually of Arabic origin. It literally means season. It is a seasonal wind that blows from continental interiors or large land areas to the ocean in winter. They blow in the opposite direction during the summer from the ocean, which is warmer at that time or cooler at the time, toward the land. Okay. Now it's most pronounced over India. Now you may hear some crazy rainfall totals. For example, Cherrapunji, India is one of the wettest locations on Earth on average because of the monsoon circulation, as well as its elevation. A result of unequal heating and cooling of land and water surfaces, that's what causes the monsoon. During wintertime, we have a massive area of cold high pressure over Asia, and this high is due to cold Arctic air and long-term radiational cooling effects. To the south, the warm equatorial waters exist with lower surface pressure, and air is going to blow from that higher toward the lower pressure. So the combination of the high pressure over Asia and that low pressure over the equatorial belt and over the warmer waters, that's going to set up a pressure gradient directed from north to south. And so you typically see northeast winds day after day dominating the regions from India to the Philippines. During the winter months, clear skies predominate over most of the region, and this is caused by the mass motion of air from higher pressure over land to lower pressure over the water. So as the air leaves the high pressure area over land, it is cold and dry. As it travels over land toward the ocean, there is no source of moisture to induce any kind of precip. Additionally, the air is traveling from high altitudes to lower altitudes with downslope motion causing the air to warm and dry. If you look at the graphic on the bottom right, this is very important. So we have these huge areas of high pressure situated in the wintertime over Asia. You have lower pressure over the actual ocean areas to the southwest of India. And then you have the Himalaya mountains, which are basically along the border there between China and India. And they get up to pretty good heights. And so you not only have, the general flow to consider, but you got to consider the altitude, the elevations of these mountains and how that plays into areas that are wet and areas that are dry. Because as air rises, it tends to increase the precipitation on its windward side. As air sinks, it tends to dry out the air column, and you get much drier conditions. So got to factor in the elevation there. Now during the summer months, the airflow is reversed from winter. So now you get this heated landmass of Asia, where it's much warmer than the ocean areas to the south. So this induces relatively low pressure over the heated landmass of Asia, higher pressure over the equatorial region, and that's going to produce a general southwest flow. The weather associated with the summer monsoon is very wet. Lots of thunderstorms, almost constant heavy rain, and gusty surface winds. So when the air leaves the ocean, it is warm and moist. As the air travels over land toward the low pressure area, it is also traveling from a lower to higher elevation. The air is lifted by those mountainous Himalayan topography and cooled to its condensation point by the upslope motion. Again, look at the elevation. Imagine now that the wind is coming from the southwest in this case. It's going to cause a lot of heavy rainfall on the windward side of the Himalayas for some of those locations. All right, so let's take a look at the general circulations. The black arrows represent the general wind regime or flow for conditions in January when we have what's known as a northeast monsoon. You get very cold high pressure systems to the north, and that's over the Asian continent. with relatively warmer ocean surface and areas of low pressure over the water close to the equator. And what you get is northeast predominant wind from land towards water in January. What happens in July? Now things change. Now we have a heated landmass over the Asian continent and a cooler ocean to the south, and the general direction, the cooler ocean, high pressure, pushing the wind from the southwest toward the northeast. So southwest winds predominate, going towards that heated landmass of Asia in summer. And there you go. Get a lot of thunderstorms, a lot of heavy rain in some locations due to this. And finally, let's talk about land sea breeze circulations. These are caused by the daily contrast and heating of local water and land masses, similar to the seasonal variation of the monsoon, but this is a much smaller scale. And these land sea breezes typically occur in summertime when you don't really have a lot of pressure gradient. There's not really a synoptic gradient. You don't really have large differences in the pressures between high and low pressure systems in the summertime because the temperature contrast is much less, and the land is heated pretty much uniformly across a large part of the U.S. All right, so during the day, the land is heated. It's going to be warmer than that nearby water area. And at night, the land actually cools quicker than the water, the air over the water area. So you get this slight variation in pressure that sets up on a daily cycle, and it's caused by this temperature contrast, how land heats up 5 times faster than water. So at night, the wind during a land breeze is going to blow from land to sea. And during the day, when you have the heated land, the air rises over that heated land. The cooler air comes in from the nearby water. That's called a sea breeze during the day. So sea breeze is going to be directed from the water towards the land. So sea breeze, that usually begins during mid-morning between 9 a.m. and 11 o'clock a.m. Local time, when the land areas become warmer than the adjacent nearby water or ocean areas. And again, that temperature difference creates an area of slightly lower surface pressures over land compared to the now cooler waters. And again, that result is a wind that blows from the water toward the land. Initially, the sea breeze is shallow, but that circulation is going to increase with height during maximum heating. Height varies from an average of 3,000 feet. It can be as thick as 4,500 feet or more in tropical regions. And it can be felt as far as 30 miles both onshore and offshore. So real interesting things. Most pronounced in the late spring, summer, and early fall, when maximum temperature differences occur between the land and the water surfaces. And here's an example of a sea breeze. So you notice the dark arrows showing the flow from the cooler air over the water area. Now the land is heated during this time. Keep that in mind. So you see those dark arrows and how they generally work their way up. The warm air rises, forms these cumulus clouds, and sometimes you get those thunderstorms develop during max heating time of the day, mid-afternoon, if you get a really fairly strong sea breeze. And then the actual, if you notice aloft, how the arrows basically point out over from the land back to the water. So it's this huge cyclonic circulation, the sea breeze. But living in the Gulf Coast for some time, I could tell you that, this is when you get those thunderstorms almost every afternoon. In the summer, the air is hot, it's humid, and you get this lifting mechanism in the form of the sea breeze that comes in. There's actually something known as a sea breeze front that extends typically 30 miles inland that can actually act as that lifting mechanism. And then there's a land breeze. Now, this typically occurs at night when you get the radiational cooling over the land area. The land is cooling much more rapidly as compared to the warmer water, the air over the warmer water. So now you get the flow of wind from the land towards the warmer water. And this is generally a land breeze. Now, land breezes tend to be weaker than sea breezes, by the way. So I definitely wanted to mention that. And you notice the circulation aloft is the opposite. So this is like a huge high pressure. This is a clockwise circulation, if you notice. And the sea breeze is a counterclockwise circulation. So it's really interesting. All right, that wraps the training up tonight on pressure systems. I hope you enjoyed the training. This is where to find Spot On Weather on social media. We're in Facebook, we're in Instagram, we're in Twitter. There's our website, spot-on-weather.weebly.com. Click there for the latest forecasts, updates, as well as the occasional blogs we put together there on the site. And then we have an amazing photo gallery. We're always adding pictures to that. We have some really interesting towering cumulus clouds over the last week that we have added to the photo gallery. So check out all the tabs. You go over to the More, click under the More tab, and you'll see a lot more options, past weather archives, weather research, useful weather links, and everything else. So subscribe to Spot on Weather for the most accurate weather forecasts. By the way, we also are on YouTube channel. Look us up on YouTube, Spot on Weather. All right, that wraps things up tonight. Thank you so much for subscribing to our channel. Hopefully you've learned something tonight. We talked about all the circulations, whether we're talking on a bigger scale with the monsoons in India and Asia, or whether we're talking about the local scales with these sea breezes and land breezes, as well as the different type of pressure systems, dynamic lows and highs, warm core lows and warm core highs, cold core lows, cold core highs, and this generally the relationship of pressure systems, thinking three-dimensionally. All right, that wraps things up. Take care, everybody, and God bless. We'll be back soon again with another training video. Take care.